Welcome to the lecture series on digital electronics. In today's lecture, we will discuss in detail about one more important combination logic circuit called multiplexer. So according to the syllabus, we will be discussing what is meant by multiplexer and the truth table of particular multiplexer called 4 by 1 multiplexer. We'll look at what is meant by a 4 by 1 multiplexer after defining what is meant by multiplexer. And we'll draw its circuit, the combination logic circuit, which will perform this operation called multiplexing. And at the same time, we'll also mention some of the applications of the multiplexer circuit that we are going to see. So what is a multiplexer? So multiplexer, the term means many to one. So the name itself suggests that it is multiplexing, or it is transferring something from many or different entities to one entity. What is that many to one or many into one? So normally multiplexing is the process of transmitting a large number of information that is present on several channels over a single channel. That is, so for example, you think that there is a large digital information that is coming from a number of channels, and you want to route the digital information that is coming from all these channels onto a single output line or onto a single line for transmission to somewhere else without changing or without losing any digital data. So that means the binary information is coming from a large number of channels, but you are provided with only one transmission medium or one channel onto which you have to transmit the data coming from all those different channels, and you should not mix up and you should not lose any data. But no need to transmit data from all the channels simultaneously. That means you can transmit the data from the first channel for some time, and then you can stop the data coming from the first channel, and then you can switch over to the channel 2, and you can transmit the data coming from channel 2 over the same output line, and after that you can switch over to the third channel, and you can transmit the data over the same output line for some time in the channel 3, and you can switch over to one more channel, and from that channel you can send the digital data from that channel over the same output line for some time. That means though you are not transmitting the data from all the channels simultaneously, you, you will be able to transmit the data from different channels onto a single output line, and this process is called as multiplexing. And the circuit, combination logic circuit, which achieves or which selects the digital information from one channel, the digital information from several sources and transmit the selected information on a single output line is called as a multiplexer, and in short it is called as MUX. You can also see here that a combinational circuit that selects binary information from one of the many input channels and transmits to a single output line. So this is the basic function or the basic definition of the multiplexer. And since it is selecting the data, or since it is selecting one of the channel to transmit the binary information, it is called as a data selector. Or I can say that it is selecting the data on a particular channel. So you are made available with a number of channels, and the circuit should select one of the channel, or should select data from one of the channel to transmit over a single output line. And then how the selection can be done? So how the selection can be done? So you'll be having select inputs in particular, which will take care of the selection of a particular channel. So after selecting a particular channel, the data on the channel will be placed on the output line. If you want to switch over to the different channel, you have to change the select inputs. So in the same way, so for example, if you have one select input, the select input can be either 0 or 1. That means it will be able to select two different channels. When it is 0, it will select one channel. When it is 1, it will select the other channel. In the same way, if the select inputs are 2, since everything is now, we are talking in terms of binary, right? So that is why any input can take only two values, 0 or 1. Similarly, if the number of select inputs are 2, then the select inputs can be either 0 0, then it selects one channel, first channel. If the select inputs are 0 1, it selects the second channel. The select inputs are 1 0, it selects the third channel. The select inputs are 1 1, it selects the fourth channel. So in the same way, you can say that a digital multiplexer of 2 power n input channels, that means there are 4, in there one select input, it can select or it can control two channels. If there are two select inputs, it can select one out of the four channels, or it can control four channels. In the same way, if there are n number of select lines, then it can control 2 power n input channels, or using n number of select lines, one out of the 2 power n input channels will be selected according to the bit combinations of select lines. So, we can give symbol for the multiplexer. So here we are showing, just see the right side diagram, and here we have shown the symbol of the 4 to 1 multiplexer. So here multiplexer will have n number of channels, input channels, and it will have only one output channels, or I can say multiplexer has n number of inputs and it has only one output. So this, here it is a 4 to 1 multiplexer, means here it has 4 input channels, and only one input channel must be selected at a particular time or at a particular instant. Then the data on that particular channel will be taken to the output line. So here, in order to select one out of these four channels, we require, so here the channels are represented with I0, I1, I2, I3. I can say the digital information. So each channel carries a digital information. So this is the information I0, I1, I2, I3. So similarly, so to select one out of these four channels, we require select lines. So are the select inputs which selects one out of these four channels. So to select one out of the four channels, since there are four channels, we require two select inputs. Two select inputs, and we designated them as S1 and S0. So if S1 and S0 are 0, 0, it will select the channel I0. And similarly, if S1 and S0 are 0, 1, it will select the channel I1. Then the data on I1 will be connected to the output line, and whatever the information on this channel will be taken at the output of multiplexer, will be provided by the multiplexer at the output. Similarly, if S1 and S0 are 1, 0, then the I2 channel will be selected. The data on this channel will be available at the output on the output line of multiplexer Y. Similarly, if S1 and S0 are 1, 1, then this I3 channel input channel will be selected, and the data present on this channel is available at the output line of the multiplexer Y. So we have one more input. We have you can see here, that is En, named as enable. So this is like to see all these logic circuits will be critically available as integrated circuits ICs. So for most of the ICs you find the enable signal. So after making this input enable, then only your circuit will work. After enabling this signal, we'll be able to use this 4 to 1 multiplexer IC. So anyway, these two select inputs S1 and S0, depending on the bits applied to this S1 and S0, we'll be able to select one of the channel, and once the channel is selected, the digital information on that channel will be placed over the output line of the multiplexer. So this is the symbolic representation for your 4 to 1 multiplexer. The four inputs, and to select one out of the four inputs I0, I1, I2, I3, we require two select lines. Two select inputs, they are named as S1, S0, and only one output line will be present for any multiplexer, and here that is designated as Y. And there will be one more signal called enable signal, which will used to enable the overall operation of the multiplexer IC. So that is we have seen here a digital multiplexer of 2 power n input channels can be controlled by n number of select lines. So here we have n equal to say 2 in our 4 to 1 multiplexer. So 2 power 2, 4 input channels can be controlled by 2 number of select lines. Then it will be 4 to 1 multiplexer. So if we have 8 input channels, that is 2 power 3, and they are controlled by 3 select lines. So in the same way, you can select out of any 2 power n channels by using a number of select lines according to the bit combinations of select lines. So in particular, we'll be discussing a 4 to 1 multiplexer in detail. So a 4 to 1 line multiplexer is defined as a multiplexer consisting of 4 input channels and information of one of the channels can be selected and transmitted to an output line according to the select input combinations. So here we have seen before we discussed that how we change the select bit lines and how we can select the information on one of the four input channels. And you can see that the selection of one of the four input channels is possible by two selection inputs or two select inputs. So since we have four channels, that is 2 power 2, the number of channels required or the number of select inputs required is n, that is n equal to 2. So here you can show it by using a small table where we have shown the select inputs S1 and S0, and we have also shown the four input channels I0, I1, I2 and I3, and at the same time we have also shown output Y. So this looks like a truth table, but includes which includes only inputs and outputs normally. So say these are the inputs and this is the output, but it also has one more input, it is select inputs or selection inputs S1 and S0. So what we are saying actually, we will be able to select the information on any of these four channels by a particular combinations for the select inputs S1 and S0. So if you see S1 and S0 can have four different combinations of bits. So they can be either S1 is 0, S0 is 0, that is one combination, and S1 is 0 and S0 is 1, other combination, and S1 is 1 and S0 is 0, the other combination, and last combination that these inputs can take is S1 equal to 1 and S0 equal to 1. And here we have shown here what we said, that by having a particular combination for the select inputs, we will be able to select the information on, or we will be able to route the information on one of the input channels to output line. So the information at any particular time on any of these channels will be either 0 or 1. That is, since we are transmitting only digital information, or will be selecting the digital information present on the input channels. So at any time on the information channels, the information present is either 0 or 1. So here see the first row, and we'll see we'll explain how this output, how we'll get the output and how the channel is selected. So if we say if we apply 0 0 for the S1 and S0 select inputs, then the channel I0 the first channel will get selected out of the four. And if on the channel I0, if a 0 data is present, then the output Y is also equal to 0, because when S1 is 0 and S0 is 0, the first channel is selected and the information on that channel will be placed over the output line. So if the channel contains at that particular time 0 information or 0 data, then output also equals 0. If at any particular another instant, if the data has, if the I0 first channel has the data bit 1, then Y also equals 1. And overall I can say that then the output line provides the information present on the channel 0, say here. Since we have started from 0, channel say 0. So the first information on the 0th channel is selected and it is available or transmitted to the output line. So if it is 0, 0 is transmitted. If it is 1, 1 is transmitted to the output line. Irrespective of whatever the data that is present on the remaining input channels. So here XX means the data can be either 0 or 1. X means either 0 or 1. So whatever may be the data present on the remaining channels, the output line, the data on the output line just equals the data on the 0th channel when the S1 is 0 and S0 is 0. So this corresponds to the first two rows of the table. And similarly, when we change the select inputs to S1 equal to 0 and S0 equal to 1, that means we will be selecting the first channel, that is I1. So now in this case, when S1 is 0 and S0 is 1, whatever the information on the first channel will be transmitted to the output line. So if the data present on the first channel is 0, the 0 will get transmitted to output line, and if the data is 1, the 1 data will get transmitted to output line. So overall we can say that when the inputs, select inputs S1 equal to 0 and S0 equal to 1, the first channel will get selected. So remember here that this channel we are considered here as 0th channel, and this channel we are considered here as first channel. So the first channel will get selected, and whatever the data that is present on, whatever the information that is present on this input line will be transmitted to the output line irrespective of whatever the data present on the remaining input lines, that is I2, I3 and I0. Similarly, if you want to select the second channel, we need to set the select inputs S1 equal to 1 and S0 equal to 0. So when you set the bits for the select inputs in such a way, then the information present on the I2, will get transmitted to the output line Y. So if the I2 channel has the bit 0, that is transmitted to output line. If the I2 channel has the bit 1, right, then 1 will get transmitted to output line of multiplexer. So overall I can say that when the bits S1 equal to 1 and S0 equal to 0, the channel I2 will get selected, and whatever the digital information that is present on the I2 will get transmitted to the output line of the multiplexer I. Similarly, if you want to select the information on the last channel, here in 4 by 1 multiplexer, this is the third channel, we need to set the bits S1 equal to 1 and S0 equal to 1 for the selection inputs or select inputs. So in that case, whatever may be the digital information present, irrespective of the digital information present on the I0, I1 and I2, only the digital information present on I3 will get transmitted to the output line of the multiplexer. So if the I3 carries the digital data say 0, the 0 will get transmitted to the output line, and if I3 has at any particular instant the digital data 1, the 1 will get transmitted to the output line of the multiplexer Y. So this happens when the S1 is equal to 1 and S0 is equal to 1. That is when the I3 channel got selected. So here you can see that the input channels I0, I1, I2, I3 are selected by the combinations of select inputs S1 and S0. So these are the combinations of select inputs. So when S1 is 0, S0 is 0, 0 channel selected, and S1 is 0, S0 is 1, I1 channel is selected, first channel is selected. When S1 equal to 1, S0 equal to 0, the second channel I2 will get selected, and when S1 equal to 1, S0 equal to 1, the I3 channel or fourth channel will get selected, and when particular channel gets selected, the digital information present on that channel will appear or will transmitted to the output line of the multiplexer, irrespective of the data present on the remaining channels or the information present on the remaining channels. So next, so this is the truth table of 4 to 1 multiplexer. Next, we will look at how to draw the circuit, combination logic circuit of the 4 to 1 multiplexer. So the multiplexer circuit, combination logic circuit can be drawn by observing this table, this truth table. So here you can see that the Y output equals I0 when S1 is 0 and S0 is 0. That is, when S1 and S0 are false, the output Y equals I0. So that is, the output Y equals I0 when S1 is false and S0 is false. So we have a term in Boolean algebra I0 S1 bar S0 bar. Or the Y also equals I1, the Y also equals I1 the Y also equals I1 when S0 S1 is 0 and S0 is 1, that is S1 is false and S0 is true. So that is Y equals I1 when S1 is false and S0 is true. That is, we have a term in the expression I1 S1 bar S0. Similarly, you can see that the Y also equals the I2 when S1 is 1 and S0 is 0. That is, Y also equals I2 when S1 is true and S0 is false. That is, we have one more term I2 S1 S0 bar. And similarly, here you can see the last case, the Y also equals I3 when S1 is equal to 1 and S1 is equal to 1 and S0 equal to 1. That is when both are true. So that is, the Y also equals I3 when S1 is true and S0 is true. So we have a term in the expression I3 S1 dot S0. So that means Y equals to these for certain combinations of S1 and S0, or when S1 S0 are true or false according to this combination. So we'll get the final expression for the output of the multiplexer, that is for output of the multiplexer in terms of the inputs channels and the select inputs in this way. So this is the Boolean expression for the output of multiplexer. See that this Boolean expression we obtained simply by observing our truth table or the function table of the multiplexer, and from this we will be able to easily draw the combination logic circuit using our basic AND or NOT gates, and that is easily possible because so this expression contains four AND terms, so we require a four AND gates whose inputs are I0, S1 bar, S0 bar. So these are the inputs. So we require four AND gates. So this is the first AND gate. So this is the second AND gate. And say this is our third AND gate. Say this is our fourth AND gate. So the first output of the first AND gate will be I0, S1 bar, S0 bar if its input are the same. So it's one of the input is I0 and the second input is S1 bar. It means so we have the inputs S1 and S0. So in order to get S1 bar, you need to use a NOT gate. So we'll get S1 bar here. So this one will provide S1 bar. So this S1 bar will be applied as the second input and S0 bar. S0 bar, so we have S0 input. We will be using one NOT gate to get S0 bar. The output of this NOT gate will be S0 bar. So if we apply the three inputs, the output will be output of first AND gate will be I1, S1 bar, S0 bar. And similarly, the second AND gate will produce the second AND gate will produce the second term I1, S1 bar, S0 bar. So with by applying the respective inputs I1, S1 bar and S0. Similarly, the third product we obtained by third AND gate with the respective inputs I2, S1, S0 bar, and fourth product can be obtained by applying the respective inputs for the AND gate I3, S1 and S0. So these four AND gates will provide the required four product terms, and we need to sum up those product terms to get the final expression for the output of multiplexer, and this can be done by using a 4 input OR gate. So this is our 4 input OR gate for which we apply the outputs of these 4 AND gate, that is the 4 product terms. The output will be equal to this. So this is the combination circuit of the 4 to 1 line multiplexer. So this is the symbol of the 4 to 1 multiplexer, and this is the combination logic circuit using only the basic logic gates. So having drawn the combination logic circuit for 4 to 1 multiplexer by using the basic logic gates, we look at the working of this 4 to 1 multiplexer using the circuit that we have already drawn. And we'll select one particular input combination as S1 equal to 0 and S0 equal to 1. So when we'll select the inputs one particular combination, for one particular combination we'll look at the working of the combination logic circuit. So that is our S1 equal to 0 and S0 equal to 1. So for this particular combination of input, then S1 bar equals 1, S1 bar equals 1 and S0 equals S0 equals S0 bar equals 0, and And for this particular combination of the select inputs, you can see the AND gate associated with the information, the first channel, that is I1 channel. You can see for this AND gate, what happens? For this AND gate, one of the input is I1, the second input is S1 bar, which is equal to 1, and the third input for this AND gate is, that is where S0, that is also equal to 1. So for this AND gate, one input is I1 and the other two inputs are 1 and 1. Actually for this AND gate, the inputs must be, original inputs are S1 bar and S0. Since S1 is 0, S1 bar is 1 and S0 is 1, so the two inputs are equal to 1. So then the output of this second AND gate will be I1 itself, because the output becomes I1 dot 1 dot 1. This simply becomes I1. So that is, so the AND gate associated with I1 will have two inputs equal to logic 1, and the third input is connected to I1. So therefore, the output of this AND gate is I1 itself. The output of this AND gate, the output of, so what is this? So the output of this particular AND gate will be I1. That means if I1 is 0, the output of this AND gate will be 0. If I1, the information, digital information on this channel is 1, then the output of this AND gate will be 1. So I can say that the output of this AND gate will be the information on the I1 channel. And you can see that for the remaining AND gates, the remaining three AND gates, 1, AND gate 1, AND gate 3 and AND gate 4, you can see one of the input will be 0. You can see one of the input will be 0. For all the three, one of the input will be your information channel. For 1 it is I0, for 3 it is I2, for 4 it is I3. But if you have the two remaining inputs, and out of the two remaining inputs, one of the input will be 0 for these three AND gates, AND gate 1, 2 and 4. Why? Because of the bit combination that we have chosen, S1 equal to 0 and S0 equal to 1. That means the outputs of these gates will be 0. That is AND gate 1, 0. So we'll be writing here for this particular combination of inputs, the output of the second AND gate will be I1 itself, and output of the 0th channel is 0, and output of this third AND gate is also 0, and output of this fourth AND gate is also 0. So these will be the outputs of the respective AND gates for the select for the combination of select inputs S1 equal to 0 and S0 equal to 1. And these four inputs will get applied to the OR gate in the input of OR gate. So 0, I1, 0, 0. So then the output of OR gate will be definitely, it will be equal to I1 itself. That is I1 plus 0 plus 0, which is equal to I1. So that is y equals I1. So if data present on the I1 is 0, then the output equals to 0. Data present on the channel, I1 channel is 1, then y equals 1. So that is, so the other three AND gates have logic 0 to at least one of the inputs, which makes them 0, and hence the R output is equal to the data provided by the channel. Thus information from I1 is available at 5. So this is, so you can verify, you can so here we have verified only the working of the 4 to 1 multiplexer for only one combination of select inputs. So we are left with three more combinations of the select inputs. That is either S1 equal to 1 and S0 equal to 0, and both equal to 0 and both equal to 1. So these are the three other combinations, and those three combinations we can apply and see, check whether the output line equals or which of the input channels is selected, and the information which of the information or the information on which input line is get connected to the output line. So here we verified that for S1 equal to 0 and S0 equal to 1, when the I1 channel is selected and the information on the I1 channel is transmitted to the output line Y. So if I1 channel has a data 0, 0 data will appear Y on Y. If I1 channel has 1, 1 will appear on the output line of the multiplexer. So this explains what is in my multiplexer, and defines a multiplexer, which also has one more name, data selector, as it is selecting the information, particularly the digital information or the binary information present on one of the many input channels and transmits it to a single output line. And for this we require n number of select lines if we have 2 power n number of input channels. To select one of the input channel, we require n number of select lines. By that you have 2 power n by n multiplexer in general, and if 2 power n by 1 multiplexer, sorry, 2 power n by 1 multiplexer, where 2 power n indicates number of inputs and 1 indicates the number of outputs, which always equal to 1 for multiplexer. So this is so in particular we have seen a 4 by 1 multiplexer or 4 to 1 line multiplexer. That means 4 input channels and only one output line. This requires 2 select inputs, and we have drawn, we have obtained the truth table or function table for this multiplexer, and we have drawn the logic circuit, combination logic circuit, by using our basic logic gates, and we have shown the symbol of the 4 to 1 multiplexer here, and we explained the working of the 4 to 1 multiplexer for one particular combination of the select inputs, and which has shown that it is giving us the proper output. And here see that some important applications of the multiplexers will be in communication systems and in telephone networks. In telephone networks will be, so this the common applications will be where we want to transmit a number of signals over a single transmission line, so to the one end to the other end, and this will be the most frequent cases in the communication systems and telephone networks, and these two will be the important applications of the multiplexers. And finally we have some of the important IC numbers for the multiplexers. So here we have given the IC numbers for the TTL family. So here the first IC is 74157, is actually a 2 by 1 multiplexer, that is a multiplexer which has two inputs and one output line, which requires only, so since there are two input lines, input lines are two input channels, we require only one select input. So but this IC 74157 contains four such 2 by 1 multiplexers in one. The 74157 contains four of such mux, 2 by 1 mux. So that is it is called as quad IC. So 74157 presents quad 2 by 1 mux. So in the same IC, four similar multiplexers are available, which are of 2 to 1 line. And similarly, we have another important IC. Its name is number is 74153, and this is a 4 to 1 mux, 4 to 1 multiplexer. Mux stands for in short multiplexer. So 4 to 1 multiplexer, and you can see that this 14153 contains two of such 4 to 1 multiplexers in single IC. So this is called 74153 is called a dual 4 by 1 multiplexer. So we are using these ICs in to build digital circuits systems. You may require more than one such multiplexer. So these ICs internally have more than one multiplexer circuits. So this 74153 has two of 4 by 1 multiplexer circuits. 74157 has 4 of 2 by 1 multiplexer circuits. So we can use as many number of multiplexers we want from that IC, even 1 or 2 or 3, whatever. So 157 we have 4, we can use any, or 1 or 4 also. In 74153 we have 2, we can use either 1 or 2. So this completes the discussion of the important combination logic circuit multiplexer. Thank you.